10:30.
10:30. So you have to wait for another 5 minutes.
Yes,
Better
sir.
So you
to
have to wait
start
for
at
another 5
10:30.
minutes.
Okay, sir.
Yeah, because the scheduled time is 10:30.
Yes, yes.
So more is going to join around that time. So I think you wait for 5 minutes and then start off.
Yeah.
So Dr. Shekhar, how are you?
I'm good, sir. How are you?
Fine, fine.
Fine, yeah,
You keep on, I keep on touch with you with your, writings and your papers.
yeah. No, we can see yours as well. Yeah. Hydrogeology is a very small community. Almost everybody, everybody knows the person.
Yeah.
And,
अभी भी काफी sir, we are still getting a lot of entries.
So you have given it, Aditya, you have given it parallelly in the YouTube.
Yes, sir, I'm looking at both the sessions. We have already got about 60 people who have joined in the YouTube session. Most of the people are directing here. I think most of the people will, once we start here, they're going to go to YouTube channel.
Actually, yesterday I couldn't get inside, so I had to see the entire proceedings by YouTube channel.
Oh. But initially you were there?
No, I couldn't get in.
Okay.
Lot of rush during 10:30.
Yeah. I also tried several times and then I could get in.
Yeah, same thing for me. I think it took for me more than 45 minutes to. So I missed the first part, the inaugural part. I missed first part of Dr. Saha's lecture. And then luckily, with the help of the students, the students helped me a lot. They send another link, and then after doing a lot of things, I downloaded this Microsoft link again, and then I could manage to. So there was a heavy rush yesterday.
There is a problem if there is the number of participants is very large in this platform.
Yeah.
Possibly,
But they say that but they say
they can accommodate plenty.
Thousands or 10,000.
Yeah, they are saying, but while trying to, there is some physical problem must be there.
No, actually, what happens, Mukunda, is
the major
yesterday
issue here
everybody
is that
tried to log in at a particular time zone.
Yeah.
So that was the problem.
That was the problem. Some of our faculty also said that they tried, they couldn't join.
Yeah, the bandwidth was entirely covered.
That is why today we insisted that all the faculty members should join before 10:30.
Before, yes.
Yeah, this is a usual practice for the webinars, that you join before, you keep your mics off, cameras off, and then the organizers come in 10 minutes before. This is normally. So yesterday I was also a bit late in joining.
Okay, so it is 10:29. I think Aditya, or what's the time?
10:29 now. It's 10:29.
Yes. So Aditya, take over from here. We are off.
I think we should switch off our speakers.
Yes.
And we should switch off our speakers and our camera also.
Okay.
Aditya, so you take over. We are switching off. Okay,
yes.
Our speakers end.
Sir, audible?
Yes, Aditya, you're audible.
You're audible, Aditya. Continue.
Actually, for my just crashed just now, but still I'm going to the mobile data and I'm started proceeding. So I hope we have roughly around good morning. to the second day of our webinar series.
Aditya, I think there is a problem on your side. Please check it out.
Can Utsav give the introduction and start the proceedings?
Has just gone.
Aditya, you can use your mobile if you.
Just before a few minutes, it was all right. No, there is still a problem on hearing you.
Sir, Utsav sir is.
I think Utsav should take over.
So Utsav sir
Is it better?
sir. He's trying to connect his computer with the link.
Am I audible?
Sir, he's five.
Can you hear me, sir?
Yes, Aditya, it is better.
Yeah, you are audible now. Please continue.
So I'm going to resume the conversation. Good morning, everyone. I would like the distinguished members of the presidency and discuss I would to start he is assistant professor in the University. He normally in so his graduation from he met and after he has more than
Aditya, am I supposed to speak?
Yes, Professor Shekhar, I think you can start the proceedings. You can start your lecture.
Thank you. Before I begin, I must thank the Presidency University, Kolkata, for giving me an opportunity to talk to young minds of the country from this platform. It's always a pleasure and honor speaking from the platform of the Presidency University. I remember in my childhood in Bihar, this was the most prestigious college people used to think of going to. And when I found one of my friends and such a scholar joining that university, I was really thrilled. So with this, good morning and namaskar to all of you. We will begin. And what I intend right now is that we want to clarify some of the fundamental concepts of hydrogeology. They're not very hi-fi, they're very basics, and many a times, many of you will start as a practicing professional hydrogeologist, and some of these concepts are not well in your thoughts. And then when you start writing, discussing, then it doesn't throw a good light. And I think this is a general knowledge of the subject earth science. It could be grasped by almost everybody. So we begin. Next. Oh, okay. So what is well hydraulics? It is a discipline which aims to understand the process of groundwater flow to well in an aquifer. Now, all this hydrogeology subject which you study and the big science and big data, it makes sense at the end of the day when you have a successful tube well which can supply either water for drinking purpose or irrigation or industrial use. It makes business sense there. It has societal value there. And that's why all of us must understand the causes and effects of a tube well on groundwater flow regime. And that's why we are going to discuss this. Okay, before we proceed to the types of groundwater flow, I would also like to, maybe the next slide and then we come back, I would like to clarify one thing to many of the beginners who might be here online with us in this webinar, that look at this drawing where you can see my mouse, and this says that these are the grains, and below this water table everything is saturated. So this all is subsurface water, and only the water below water table is groundwater. So groundwater is not all the water below surface of the earth. It is only the water which is in the saturated zone. So when we say that we are trying to understand the groundwater flow, what we mean is flow in this zone, saturated zone, not the unsaturated zone. So what all the well hydraulics and whatever we will be discussing here in this lecture will be centered around here, the groundwater zone. Then the next, before I go to my previous slide, you have a look here. See this particular figure. This was made by me for trade fair way back in 2007. This is a tube well which pumps water from an aquifer. And you know the effect of this? It makes a cone of depression. It makes a cone of depression. And this is drawdown. I have a question. Why a tube well makes a cone of depression? And then the second question, why it is conical in shape? I'll elucidate and then answer, thinking that you are in my class. I'm asking this question to me. Now, look here, in this cone of depression, this is all unsaturated. What it means? That initially, this was all saturated. When you started pumping, it desaturated the aquifer to yield water. Now, when it desaturated, ideally the water should have flown from sides and filled in this. But the problem with groundwater flow is that it flows at a very slow velocity, maybe 0.5 meters per day, maximum 8 meters per day or something like that. So when you pump this out, there is a call created here. I am unsaturated, please flow from sides. But this is a laggard. It travels at a very slow speed and it's not able to replenish this. And that creates an unsaturated zone here. And that is cone of depression. Then the next question, which I expected you to ask, I'm trying my level best to make it a dialogue mode with questions from my side and answers from my side only. That why is this conical? And then my class used to wonder, oh, this is so. And the best thing which I will say, ask two of you to put your handkerchief in hand and then put my pen in that, and it makes a conical depression. Because the tube well is cylindrical, and that's why it's a conical depression. If the tube well was a big rectangle, then it might not have been a conical depression. It would have been something else. The geometry of the cone of depression is controlled by geometry of the tube. In the the groundwater regime. Now, then this, can I go back? Yeah. So coming back to types of groundwater flow, see, any flow is it can be a one-dimension linear flow. So it's a one dimension, two dimension, three dimension, something like that. Necessarily it will be one dimension and then two dimension, three dimension. You can remove this word linear from here. But when you pump a tube well, this water was flowing like this. You look at my mouse from left to right. Okay. And then suddenly you have created a point stress here. So what happens? Water from all sides locally converges to this point, and that is radial flow, a series of linear flow converging to a point. Now, in nature, many a times you have a river like this, which is fed by groundwater. So it's not necessarily that it will flow in one direction. Maybe it is gaining from both banks or one bank. And this is an unconfined aquifer. And this is a confined aquifer. Most of the time in a confined aquifer, yes, most of the time, yes, that's fact. As long as it is confined, the water flows in one direction. We will discuss this, the confined and unconfined aquifers. And then you might be wondering why I have made these all drawings. Yeah. This is a purged water table in unsaturated zone, which is often tapped in this guise. And this is well interference. That is, one tube well was pumping, and then another tube well came in vicinity. And like an Indian marriage, they have tied the knot here and interfere into each other's life. And then there is a greater depletion of the water table. So let's move ahead. All of you must be aware that you have mainly two types of aquifer: confined, unconfined. There can be leaky, semi-confined. Now I must clear in the beginning that it's a two different system. The hydraulics is different, the well hydraulics is different, the flow regimes are different, the physics is different. And most of us goof up many a times by clubbing the two together. So we must be very careful. And this is a confined system where you have an impermeable strata, an impermeable strata. This is a closed system locally. The system locally is closed, means a drop of rain which falls here does not goes into this aquifer here. It is recharged somewhere in a far off area where it ceases to be confined. And yeah, that was for water. And then you look at this. If the pressure head in this confined aquifer, it is here this level, it is here this level, it is here this level. So the head is decreasing to my left, and so the groundwater flows from right to left in this direction. Now in no way this pressure head, as long as it is above bottom of the top confining layer, affects this groundwater flow. It changes from here to here. As long as the slope is here, it will keep flowing like this. It changes from here to here. As long as the slope is to my left, it keeps flowing like this. The two are disconnected. The two are disconnected. There is a cause and effect relationship, but there is no direct interference. There is no direct linkage. It is unlike an unconfined aquifer, where the saturation top or the water table head always interferes with this flow line. And that is the big difference. And there are a lot of pressure dynamics which is different. So, and this is a confined aquifer. The previous one was not being pumped. There was no pumping. There are just holes, cylindrical holes put in. They're not being pumped. And here, one of them is being pumped. And when you pump this out, what happens? The piezometric surface declines locally, creating a cone of depression, and the water from all sides flows in. Now, a class, if it was here, it should have asked me a question. You just explained that this cone of depression is a desaturated zone, but here it has nothing to do. Yes, when I explained that, the figure was that of an unconfined system. There was no confinement. Here, it is a confined system. So then the next question is, then what makes this cone of depression? And what makes is the pressure gradient created on account of water being pulled out through this cylindrical hole through this tube well. So when you pull this water out, there is minimum pressure here, and then somewhat more here, somewhat more here. Here it is equal to the original pressure, the initial condition, and that creates the drop in head like this. And so now you will appreciate that the hydraulics of confined and unconfined aquifer is totally different. The flow regimes are different, and the hydraulics is different. So let's move ahead. Yeah, this is very simple. This is Darcy's law, where it says that the flux, that is Q upon A, is hydraulic conductivity. This is along x direction, so it is Kx divided by hydraulic gradient. I don't know, by writing such a simple equation, Darcy became so famous. It's an empirical relationship. I wish someday we will also do something like that and give a fundamental equation in science. But anyway, we all use this. So this is x along x, y along y, z along z. Next. Now, if you read this heading, it says a steady unidirectional flow in a confined aquifer. I have not defined what is steady. Somehow the sequencing puts it later, but we will introduce it right now and then discuss in detail later on. Look, any flow regime, any state always endeavors for a steady state low energy condition. Why groundwater is flowing? Look at my mouse. Why it is flowing from right to left? Because it always wants to reach an equilibrium condition. And that's a nature, that's a nature's endeavor. That's a human endeavor. All of us always wants to reach a steady condition, whether it may be in a relationship with your girlfriend or in a family, everywhere you want to reach a steady state condition. Now, in a groundwater flow regime, the steady state condition is reached when recharge equals to discharge. Now, not how it is, then you will ask me how it is physically manifested. How the hell I know when recharge equals to discharge? Who is going to compute this? Okay, you need not compute this. Your best manifestation is this head, this piezometric surface. The moment it does not change with time means for so many years there has been no change in recharge and discharge, and the steady state condition has prevailed. It is like a successful Indian marriage, that when for so many years, because of so many external forcings, still you are a happy married couple. That is a steady state condition in my view. Maybe you can have a different opinion. Okay, then this is a unidirectional because the flow is from right to left. Now, look, what I'm trying to say is that if I look at this, can I use Darcy's law here? Let me examine. This is one of the Darcy's experimental setup. Though the original was never like this. Just take a sip of water and then come back to you. Yeah. Now, if you look at this Darcy's experimental setup, this is a manometer on the right, manometer on the left. This is the this is one head of the water table head, a piezometric, it's a water head. This is another water head, and this is the difference, and this is over delta L. So Darcy's law says that this velocity, Darcy velocity through this tube, or the flux through this tube, is delta H upon delta L, where delta H is the head difference and delta L is the length along the flow direction. Please note this down. This becomes important because this will trouble us later on when we go to unconfined aquifer. What is delta L? Delta L is the length along flow direction. Now come to this. This is an analogy. This unconfined aquifer is an analogy. How it's an analogy? Yeah, this is top confinement. This is top confinement. This is bottom confinement. This is bottom confinement. This is 1 manometer. This is 1 manometer. This is another manometer, another manometer. Delta H is this, and it is along this length. So I write that flow lines are restricted between the confining layer of confined aquifer and piezometric surface lies above the upper confining layer. Yes, that's fine. Now this has nothing to do with Darcy's law, but still I have put it here that the symmetry of flow lines are controlled by symmetry of the confining layers, means that if your confining layers are like this, then the flow lines will be like this. If it is like this, and like so. So this condition is similar to Darcy's experimental setup, and as such, to quantify the confined aquifer groundwater flow, we can use Darcy's law. Yes, perfect, because this is Darcy's law is an empirical relationship, and this is an analogous relation. So we say that without any doubt, we can use Darcy's law to quantify flow in a confined aquifer, where V is a specific discharge. Sometimes I use Q for this, sometimes I use V for this. That's my problem. Please bear with me. I'll correct it sometime later on in my other presentations. Yeah, because the presentations are made in a series of sittings, and then I forget what about the last term I have used for V. But I take care that I must define it every time. So V is a specific discharge, K is hydraulic gradient, DH. It should have been delta H by delta L, but I couldn't put that here because of the limitation of PowerPoint. So I have put it DH upon DL. Anyway, as per Darcy's law, because delta H varies linearly along delta L, it can be DH upon DL. So let's move to the next. This is an unconfined aquifer. Yeah. Why unconfined? Because there is only bottom impervious, top is here. This is not impervious. Forget this actual water table. Say this is a water table, and this is Darcy's setup. Now, what are we missing? First, in Darcy's setup, the water table head was in no way connected to the saturated thickness. Here, the water table head is top of the saturation thickness. No problem, no problem. That's fine. It's a head. So head is here high, head is here low. Then the biggest problem is that you are on the land here. You are on the land here. So if you make a tube well or a borehole here, and if you make a borehole here, you can say this is the water table head here, and this is the water table head here. And you know this distance, delta L. But mind you, this delta L is not this delta L, because this delta L is the direction along groundwater flow. And here the groundwater flow is like this. It is, oh, just let me go back. Yeah, it is like this. Yeah. So if you, even if you convert this into a computed straight line, the flow is not like this. So this is the real delta L is from here to here. And that is a problem. That is a problem. Then second, in Darcy's experimental setup, all flow lines are horizontal like this. But here it will be like this. I've slightly exaggerated it. So let's read what are my thoughts on this. In unconfined aquifer, the water table surface controls the flow lines. In confined aquifer, it was the confining horizons. Here, it is the water table top. And then delta L of Darcy's equation should be a straight flow line in direction of groundwater flow, which is not so in case of unconfined aquifer. Now, believe me, for time being, I will prove it mathematically after a few slides that the water table top is parabolic. So this top is parabolic, rather water table top is curved and parabolic. I've written, we will prove it. Moreover, forget this. This is a assumed velocity vector. The actual velocity is like this. Now, this drawing has been exaggerated, so they flow at a greater inclination. Might be in reality it will be like this. And so finally, if this is not analogous to this, can I use Darcy law in unconfined aquifer? No, not allowed. I have to think. How do we use that? That is where Dupit's assumption come. Many of you might have done your post-graduation in hydrogeology. I also did a major in hydrogeology, worked in Central Groundwater Board for 8 years, and I could really understand Dupit's assumption only when I started teaching hydrogeology. That's an honest confession. Teaching is the biggest learning process. And I must say that when I was asked to teach this subject and teach Dupit's assumption, I started reading it again. And then I could understand in a better way. I have talked to many professionals and they say, yes, we are not clear on this. So let's look at it carefully. Dupit's assumption, and what was Dupit's assumption is nothing. He just wanted to facilitate use of Darcy's law in unconfined aquifer. Because Darcy law is a very simple and universal law, and Dupit saw a merit that if I could make some small assumptions and then use Darcy's law to quantify groundwater flow in unconfined aquifer. And what was Dupit's assumption? That he said, hang on, why you are breaking your head? First of all, if I have to estimate the groundwater slope from Bihar to Kolkata, it will be 1 degree, not more than that, under normal flow condition, or maybe 2 degree. Groundwater slopes are very, very, very less, within 5 degrees, 6 degrees, except in vicinity of a pumping tube well. Yes, that's a rider. Except in vicinity of a pumping tube well, the natural groundwater slopes or water table slopes are very small. So he said that this difference is not big. Why can't I assume these lines at an inclination to be something like this? People said, okay, Dupit, go ahead. That's fine. We have assumed. We agree if this angle is very less, so you can do that. Then the next is, many of you won't be understanding, the students, that he said the velocity of flow can be assumed to be proportional to the tangent of hydraulic gradient instead of sine, as in case of Darcy's law. I will explain this. I understood this, frankly, after teaching my first semester at master's level. When I was grilled in a class by intelligent students, and then I said, look, I will work on it with trigonometry and mathematics, and I thank those guinea pigs, my class students, who helped me improving my understanding on this. And I think now it's fair enough. Now, what I have done is, you won't find this in book. This is from Fetter, Todd, and these are my modifications to help you understand this. Now, this is land surface, so that is fine. This is land surface. I have made a parallel to land surface here. Okay. and this is the head drop. I think this is the equivalent computed line for this. It should have been somewhere here. So please just bear with me for a small mismatch in drawing. So this is this. So this is delta H, and this is the actual groundwater flow line, delta L. And this L should be here, and this theta should be here inside. So this L is here and this theta is here. Now what Darcy law says, that Q, I put it here V, that is Darcy velocity, is K delta H upon delta L, that is length along the flow direction. Now delta H is perpendicular and delta L is hypotenuse of a right angle triangle. So Darcy law originally in an unconfined aquifer says that V is K delta H upon delta L or sine of this theta. P by H is sine. So as per Darcy's law in an unconfined aquifer, K is delta H upon delta L or is K sine theta. Now what Dept said, he was a wonderful man. I must congratulate him for his simple approach in life. He said, look, this theta, if it is very small, then this delta L and L will be same, will be approximately same, maybe a very small amount of difference. So why not assume that approximately this L is equal to delta L? And then he said, you write your equation, Darcy equation, as delta H upon this L. Why he wanted this L? Because it can be measured on surface, land surface. This cannot be measured on land surface. And so I said for a small theta, then where is this? It's here or no? Shall I put it down? Yeah. So estimating delta L from surface is difficult. Hence Dept's assumption says that for a small theta, delta L is approximately equal to L. And so if you write Darcy's law, it says K tan theta for a very small theta. And this is what Dept writes in his classical paper, that velocity of flow can be assumed to be proportional to tangent of hydraulic gradient instead of sine. That is tan theta instead of sine theta. And so if you do this, then he says, okay, then the problem is solved. Why? Because delta L I am measuring along surface, delta H I can measure along two wells or boreholes, and I have assumed that velocity is like this. So this delta L is approximately along groundwater flow direction. And then Dept said you can use Darcy's law for quantifying groundwater flow in unconfined aquifer. Now, when we say this, I must put a rider that within radius of influence of a tube well pumping at high capacity, this theta is very high and Darcy law is not valid. So if you are going to use Darcy law, then it will have its own problem. And that is why other equations were evolved. But later on, in a steady state condition, we will be using this Darcy law. And then I will answer that why we are using this. So with Dept's assumption, we can quantify flow in unconfined aquifer using Darcy's law. I hope you are convinced. Now look at this drawing which we have used. Yeah. This is a vertical section. So in 3 dimensions, it is something like this. So this is a unit width. This is unit width. So discharge, this discharge from here per unit width, let us say as QW, as per Darcy's law, it will be minus K into H. Why H? Because here H is the height, this is the height, and this is 1. So H into 1, area is this into this. So this dimension is 1. So k into a, instead of a, it becomes h. And dh upon dx is variation in h along x direction. So if that is fine, let's come to the next slide and say I rearrange it q into dx minus kh dh. It's a very small integral. Anybody who has done class 12 can do this. And so it says qx, if you integrate h dh, I have not put this here because that integration sign was difficult to put in this PowerPoint. So if you put an integration sign here, an integration sign here, integration of h is h square upon 2, and integration of dx is x. So the equation reduces to qw into x minus k h square upon 2 plus this constant. Forget it for the time being. And if you rearrange this, you can write a relationship in terms of, don't go on this, x and h. And then ultimately you will find that from this equation, it says that h varies along x as a parabola, because this is equation of a parabola. And then using the same Darcy law, which we were not able to quantify groundwater flow, we made some assumptions and did a basic quantification, and we have proven that the water table top is not a straight line. It is parabolic. It is not a straight line. It is parabolic. And every time we assume it to be a straight line. So now, in a system equilibrium perspective, you can have a steady state, equilibrium condition, transient flow, non-equilibrium condition. And what is steady state groundwater flow? It refers to a flow condition when magnitude and direction of a specific discharge is nothing but Darcy velocity remains constant with time. And why it happens? Because there is no addition or withdrawal from the aquifer storage, and equilibrium has been reached between recharge and discharge. And how it is manifested? It is manifested by position of the potentiometric surface and the hydraulic gradient, which remains unchanged. In a nutshell, when input and output from the aquifer is reached in an equilibrium condition, the water head does not change, and that is a steady state condition. And don't go on this, just have a look. This is a partial differential equation. This has been derived using Darcy's law for heterogeneous and anisotropic aquifer. Now, many of you might be interested in knowing that how it makes a difference. See, what is aquifer heterogeneity? Aquifer heterogeneity refers to a condition when the parameters changes in space, and isotropy or anisotropy is a directional property. Why it is heterogeneous and anisotropic? Because kx is varying along x. Kx is not a constant. It has been put in the bracket, and it differentiates with x. It means that kx is changing along x direction, which means that in a space kx is not constant, so it is heterogeneous. Why it is anisotropic? Because kx, ky, and kz, if it was isotropic, they should have been equal to each other and might be 1k. But we have put kx, ky, kz, means it is anisotropic. Then somebody will ask why this is 0. Yeah, because on the right hand side in the general equation you have dou h upon dou t, that is differentiation of dou h upon dou t, because head we have defined that in a steady state condition head does not change with time, and so when you differentiate a constant head with time it becomes 0. Now when you have a homogeneous and isotropic aquifer, what happens? This kx becomes equals to ky, becomes equals to kz, and then in isotropic, Kx equals to Ky equals to Kz, and in homogeneous, they won't vary, so they will come out. So K comes out, gets divided by 0, becomes 0, and then it becomes differentiation along dx of dh upon dx, which is as good as dou square h upon dou x square, and like that. So now what is a transient condition? Now transient is unlike a steady state. It refers to a flow condition where the magnitude or direction of a specific discharge changes with time. Means the velocity changes with time. Then it involves change in storage. Means aquifer has not reached an equilibrium condition. The recharge and discharge is always, the recharge is not able to cope up with the discharge maybe, and so water level is declining in one condition, and in another maybe recharge is more than discharge and the water level is rising. So things like that. And the best manifestation is that the piezometric surface or the water table is not constant with time. Yeah, many of you might be a research scholar, and your life condition is very similar to that of a transient flow, non-equilibrium flow, where it keeps changing with time and with your struggle to get a job and get a publication. So this was the general equation, where on right hand side in a steady state condition you had 0, because this h in a steady state condition becomes constant, and so this becomes 0. Don't break your head on this, because I put this because I do groundwater modeling and these equations fascinate me. But yes, at a master's level you are supposed to know this. Okay, so radial flow to a tube well. What makes sense to us at the end of the day is that my tube well should give potable drinking water and in sufficient volume for me to suffice my needs. Now I have already defined radial flow of a tube well refers to groundwater flow condition where they flow from all sides. They are nothing but a set of linear flows. There are many mathematical equations which quantify radial flow, but they have big assumptions. And we must know that this radial flow is best quantified using this equation. But using this equation is very tough. And so we will go to some analytical models or simpler equations and try to understand the groundwater flow. So for a radial flow to a tube well, you have a steady state, transient. These are decorative scientists, time, who derived the equation for confined aquifer, and so he got his name. Then Dept, who derived the equation for unconfined aquifer, and then this is one of the after Darcy's law. This is one equation which is most widely used. So now this drawing has been taken from Todd's book, and just to I have made a few additions like static water level, pumping water level, and saturated thickness, things like that. Now look at this. This is a pumping tube well. This is a pumping tube well, and these are two observation wells. Water is being extracted from here. Nothing is being extracted from here. They have been just made to monitor the piezometric heads. Nothing. They are observation stations. But here water is being pumped. Now before we go, we must know that when you pump a tube well, the maximum extent to which its cone of depression goes, this is radius of influence. It is like you know, those tigers domain in a jungle, that each tiger has a defined territory, and each dada of a muhalla has a defined territory. So each pumping tube well has a defined territory at a given discharge. So this is the radius of influence of this tube well. The other side is like this, but it was too big. It will be too big to make it here. And this, the diameter of this tube well is 2 RW, so radius is RW, and this is at R1 distance, this is at R2 distance, and the potentiometric head is here, H2 and H1. Now, do I have another? Yeah, here, and then I'll come back. Look at this. What is the surface area through which groundwater enters this tube well? I guess you have answered correctly. That is curved surface area of a tube well. And what is a tube well? Tube well is a cylinder. So this groundwater enters through curved surface area of a cylinder at this point. Now, in this flow domain, within this radius of influence, when this radii is R, then the curved surface area is 2 pi R, and this L, that is B, 2 pi R B. Now, here also, if in 3 dimensions I imagine, then there is an imaginary big cylinder through which this groundwater from all sides are flowing in an endeavor to reach this tube well. So at distance R1, the area through which this groundwater is flowing is 2 pi R1B. And likewise at distance R2, 2 pi R2B. So what I wanted to convey is that the area through which groundwater flows in this tube well at any point, you say, within the radius of influence is a curved surface area of a cylinder, because you have made the tube well cylindrical. Now coming back. Okay, and then we must assume that this is a 2-dimensional flow to a tube well which is centered on an island. That means it is a standalone system, not being interfered by neighbors. Another tube well, aquifer thickness is uniform. Yes, this makes a lot of difference. I wish it was a class. I would have taken one class on this. Why the well should penetrate the entire aquifer. And then initially piezometric surface is assumed to be horizontal for simplification purpose in mathematical computation. It has a small slope. So let's come back here. Now, so when I want to know that what is the curved surface area through which groundwater is flowing, then it is 2 pi RWB. At this distance, 2 pi R1B. At this distance, 2 pi R2B. Because then, as per Darcy's law, Q is Ka dH upon dl. That is hydraulic conductivity into area into hydraulic gradient. Why I was worried about this 2 pi RL and 2 pi RB, because I wanted to know this area through which groundwater is flowing. So for sure I know that in this confined aquifer case, this area is 2 pi RB. And K is an aquifer parameter. This dH upon dl here will be dH upon dr, because r is the radial distance. Now let's see what I have written. Yeah, that's curved surface area of cylinder. Yeah, that's fine. Okay. So this is okay. Another thing important, I must introduce it here, is that this L of a curved surface area, which is your 2B, this is constant in a confined aquifer, because no amount you keep extracting water as long as it is confined, the saturated thickness remains constant, and so this B remains constant. But this is not in case of an unconfined aquifer. Later on you will see, and that introduces one more variable. So in case of a confined aquifer, the length of cylinder is fixed, that is B is fixed thickness of the aquifer, while R is a variable. And so you can write Darcy law like this. Yeah, Q equals to 2 pi dr dh upon dr, and then you rearrange it like this. Why I am rearranging? Because I want to integrate, so I have brought R with dh upon dr, and now it becomes very easy. Q is a constant, 2 is constant, pi is constant, k is constant, b is constant. What is variable is R. So I have brought all the constant this side and brought this dr from denominator here. And so it is basically integration of 1 upon R dr and dh, which is nothing. So it's written here, integration of dh and 1 upon R. So integration of 1 upon R is log n R, log of natural log of R, and integration of dh is h. So if you put the limits as h2 minus h1, ultimately you get the time equation for a confined aquifer under a steady state flow condition. Under steady state flow condition. Now, I wonder if I had some genius student sitting in my class, and of course not the one who fears to ask a question. Yeah, your questions give me kick. Then he should have first asked a question. Sir, why you have skipped this minus sign of Darcy law here? In Darcy law, if you remember the earlier slides, most of the time we say Q equals to minus Ka dH upon dA. Then his first question would have been, who gave you authority to skip this minus? Yes, I must explain. I tell like this because my students have asked like this in class, and then we have opened books and then we have discussed. Okay, look at this. Darcy law, what it says? That groundwater flows in direction of decreasing head, and distance is measured. So if initial head is here, let's say 2 meters, final head is 1 meter. So the head you measure like this and distance you measure like this. Okay, and that's why you have a minus sign, because H2 minus H1 is always negative. But in a tube well flow regime, the way you are measuring is different. In Darcy's law, you had measured length along the direction of headfall. Here you are measuring R away from the tube well, that is from center to periphery. So this vectorial difference introduces another negative sign which negates that negative sign, and for well hydraulics and groundwater flow to a tube well, this minus vanishes. It is only valid as long as you are using radial distance measured from center of the tube well to its periphery in the direction of increasing head, not decreasing head, as in case of Darcy's law. So I hope this satisfies. And then the second question somebody should have asked, just take a sip of water. And the second question somebody would have asked is that, come on, here is fine, but how will you do it in unconfined aquifer? You said that Dupit's assumption is not valid. Okay, I will answer that when we come to unconfined aquifer. It's a still confined aquifer. Okay, so all very simple mathematics. Now, in an unconfined aquifer, you see the difference. What is the difference? The confining layer has vanished. I have a better figure which I just picked up for this webinar. Yeah, it's here. Yeah, this was just introduced in slides 2 days back. Look at this. This is a typical unconfined aquifer. This is a saturated zone. This is a tube well which is pumping water out, and this has made a cone of depression. And these are This is one line here, there's another line here, which is nothing but the saturated thickness. The first difference I want to introduce between the well hydraulics and groundwater flow regime of a confined and unconfined aquifer is that here in unconfined system, the saturated thickness changes. It is constant outside the radius of influence, but within the radius of influence, here it is H1. If it is 3 centimeter in here, then H2 will be 2 centimeter and like that. So the saturated thickness in confined aquifer, B was a constant. If you have forgotten, it was a constant here. It was a constant here, not changing because of change in because of these cone of depression. Here it is a variable, and that makes a lot of difference. That makes a lot of difference. Second, okay, that's a tough answer. That why you are using Darcy law? Why you are using Darcy law to quantify this? Because you can see I have written Darcy law. Because this is an exaggerated drawing. This is an exaggerated drawing. And many a times this actual aquifer loss, if you just exclude the well loss of a tube well in an unconfined system, is very less. And so the gradient is not very high. The curvature in the flow regime is not very high. And so we use Darcy's law. And to be more precise, we don't have another equation to use right now. You can make one and we will use that. So that leaves a scope for working. So let's come back. Now this is the same tube well. You're pumping from here. This is static water level. So this is one water table. This is another water table. Now again, this gives me liberty because R1 I am measuring from here, R2 I am measuring from here, and the head is falling against that direction. So I will remove that minus from Darcy's law. The assumptions are same. I will explain this also, why this penetration after some time. Now the water flow is curved surface area of a cylinder. Yes, here it flows through this. If you imagine a cylinder like this, then here the water flows through an imaginary cylinder where the curved surface area is 2 pi h1. Here it flows through an imaginary cylinder where the curved surface area is 2 pi h0. Here it flows through an imaginary cylinder where the curved surface area is 2 pi h2, if we say h2. So the problem is that this length of the cylinder, which was a constant in a confined aquifer, has become variable here. And when it has become variable here, it will have to be integrated. And so I think this is all I have explained. So we can write Darcy's law as Q equals to K 2 pi RH dH upon dr. And this 2 pi RH is nothing but the curved surface area of a cylinder where this H is variable. We rearrange it as 2 pi K RH dH upon dr. And then you just put this Q upon, because why I put this Q is constant, 2 is constant, pi is constant, K is constant, D upon R and H dH. So you take this on left and bring this here, and then you integrate. It gives a different equation, and that equation is integration of H is H square upon 2. So if you limit H2 and H1, so it becomes H2 square minus H1 square. And likewise, integration of 1 by R is log n R, and you ultimately get this equation, which is Dupit's equation. The point is that the well hydraulics of a confined and unconfined aquifers are totally different. It is because the confined aquifer is a closed system where the water level head or the water head that does not change with respect to pumping, and the saturated thickness remains constant. In an unconfined system, it's an open system where the saturated thickness changes with the water table. and that makes a two different pressure systems where the flow regimes have subtle differences. Most of the time as a hydrogeologist, we mess up with the two and try to use one equation for the other. We can use that. Yes, there are ways, but with an assumption, not directly. Okay, so no, before that, the partial penetration I must introduce, so the students will have this inquisitiveness. I think I can use this, or maybe, no, this is a better one. Yeah. Look, why you say that the well should fully penetrating means the slot should be from top of the aquifer to bottom. Now, what if I just make a tube well like this, where the slots are till here only? What will happen? That this will forcefully introduce curvature in flow lines. Means this flow line, which was this, let's examine this flow line, which was going here, will now enter the tube well like this. It will enter the tube well like this through the slots. And the moment you do this, first, Darcy law is valid for laminar flow. There are many questions on this. I will not open the Pandora box right now. I wrote one of my first papers on this, but still this will violate the laminar flow of Darcy law. Second, whenever water takes a longer path like this, there will be a head loss because it will have to fight the resistance of the aquifer. And so this head loss here will be more, and likewise. So you will not get a true assessment of the aquifer response. And thus, when you are doing any testing or something like that, you must have a full penetration. Before I go to the non-equilibrium condition, I must say, speak a few things about pumping test and then come to this. Okay, so what is a pumping test? Now, pumping test is nothing. It's a routine groundwater exploration exercise to estimate the aquifer and to estimate its parameters. So what we do? We make a borehole, we make a test borehole, exploratory borehole like this. It's a tube well like this. We make in earth. Then we pump this out. The moment we pump this out, we develop this into a yielding tube well. After we do this, then we want to know that what is the parameter of this aquifer. Means what is its transmissivity, what is its hydraulic conductivity, what is its storativity if this is a confined aquifer. We want to estimate that because that helps in further quantification of the groundwater flow regime if you are aiming to attempt that. And so before any pumping test, we do a well performance test. That's not an aquifer performance test. Many of the young researchers goof up there. Its well performance test is just meant to assess performance of the tube well and see that what amount of head loss is because of act of making a well, that is well loss. So well performance test is done as a preparation for aquifer performance test. And then we go for an aquifer performance test where the arrangements are like this. You have a pumping well which pumps water, and then you have observation wells at distance R1, at distance R2. Now you as per your experimentation design, you will pump this well out, pump the water out from here, keep monitoring the water table head here, keep monitoring the water table head here, and say you started pumping. Initially it was here. Say after 3 hours the water table head is this here, here, and here. After 5 hours, it is here, here, here. After 20 hours, it is here, here, here. Then you make a comment that after 3 hours, a steady state condition has been reached in this groundwater flow regime within the radius of influence of this tube well. And so with this data, you can use this data to estimate hydraulic conductivity of the aquifer. With the equation you have derived, hydraulic conductivity, K, I have made the principal. So this cross multiplies Q ln R2 by R1 divided by pi B2 minus square minus, this is not B, this is H. There's a typing error. This is H2 square minus H1 square. So, but there is a limitation of a steady state pumping test with a steady state condition. Your equation does not have a storage parameters. And that is why if you want to have the storage parameters estimation, you must have the transient data before this condition was reached. In unconfined, this is a totally different story. But in confined, you can use that. So now see, before we go to this transient or unsteady state flow in a confined aquifer, I must say that the steady state condition was easiest to derive mathematically. The flow regime was simplest to understand because the condition was a steady state and this piezometric head had stabilized. We could quantify. Why we could quantify? Because in a steady state condition, this piezometric head was not changing. But in a transient condition, every minute this diagram changes. It becomes like this, then after 2 hours it becomes like this and like this, or maybe like this. So to quantify a system which is changing regularly is tough, and for years hydrogeologists were struggling, and there was a hydrologist, Thais, who came out with an equation which is being widely used. I must tell a small part of this story. That Thais equation was never written by Thais. He was struggling, and then he went to a mathematician friend of his. He knew that heat flows from higher temperature to lower temperature. So he was an engineer. So he said, okay, I will make we have an equation for heat flow. I will use that in groundwater flow regime. He had this idea, but he never knew how to write an equation. And so he went to a mathematician friend of his and he wrote an equation like this. This mathematician, Thais, like a old gentleman scientist, went to him and said, okay, you will be my co-author. And the mathematician said, hang on, this is very trivial. I won't be co-author. This is all stupid science which I do daily. This is not big science. And he refused to be co-author of the paper. It's written in Fetter's book. You read it. And then Thais wrote that paper as a single author and got credit for this equation. So with this small background that you should never give up your small contributions. You can become a legend. Thais become a legend. Nobody knows that mathematician. Thais wrote an equation that H0, this is the head, and this is H. So he said that for H0 minus H, that is head difference, this head difference, which is a drawdown, the equation is an analogous to heat flow. It's Q upon 4 pi T integration U to infinity E minus U upon U du, and U is R square S by 4 TT. Now this looks complex, but it's fairly easy. Now this Q is discharge of the tube well. This is discharge of the tube well. Pi, all of you know. T is transmissivity of the aquifer. It gives an estimate of the velocity or the transmission of the water. And then this S is storativity of a confined aquifer, that is storage coefficient, how much of water per volume of the aquifer it can store or yield. This R is this radial distance. Let's say if you are here, then this becomes R, and this U is from here, and this whole is known as well function. So let's forget this, not put this complex mathematics. H0 minus H is Q upon 4 pi T WU. This is a simple equation. Now this is also, this can be written as drawdown, because this minus this will give a drawdown, or H0 is this. So at any point, initial head minus the current head is a drawdown. So this becomes a small s drawdown. So you can write this equation as, from this equation, you can estimate T, Q upon 4 pi H0 minus H WU, and you can estimate S, 4T T UT by R square by rearranging this. The question is, you will ask me how? Yes, you will ask me how. You just said from an equation, I can estimate transmittivity of an aquifer and a storage coefficient. It is here that a purpose-built pumping test is designed. And when the purpose-built pumping test is designed, what we do, we have a pumping well, and then we have one observation well. Let us say, start from one observation well here. And as a hydrogeologist in Central Groundwater Board, if you are working or if you will work, this will be your routine work in exploration. So you pump this out at a constant discharge. So Q, you know, you measure, so Q, you know. Then what happens is that this drawdown every minute, and then after some time, 5 minutes or 10 minutes, I was fortunate in Groundwater Board, Central Groundwater Board, to do this pumping test for so many tube well, well performance for 100 tube well, and long duration for maybe 5-8, aquifer performance for 5-8, and then professionally as an academics we did some for 4. So then you monitor this drawdown with respect to time. It is here that an officer is assigned. I must say, if you become a hydrogeologist in any of the organization, please don't put your contingent labor on this work. This is a crucial observation. You must take yourself or put a DWLR, digital water level recording device. And so you monitor the variation of drawdown with respect to time here. So you have a time, T, this T, you have this drawdown, and then what else? WU and U. You will say then from where this will come. Yeah. I think I have time. Yeah, I have time. So just a sip of water and then we come back. We will just go ahead. I believe that by now you agree that if you just put observation well and a pumping well, we can solve this equation, and we will solve it in the easiest possible way. Now this is Q is constant discharge, H minus R is distance, S is coefficient. I think I have said this all. Yeah, there are a set of assumptions in any master's student in Delhi University. We spend 2-3 days discussing these assumptions because everybody keeps asking, what is this? Why you said took this assumption? Why you take this assumption? And so at least 2 to 3 lectures are spent this. If I have time or you can raise a question, I will love to answer why these assumptions are there. I will read it for you. The aquifer is homogeneous and isotropic. Yes, because else you cannot quantify. It becomes very difficult. Then it is of infinite areal extent. Again, the same thing, well penetrates the entire aquifer. I think this we have explained. T is constant. Yes, if it varies, I cannot derive. Well has a very small diameter because to avoid a storage effect. Then the water is from which is removed is instantaneously replenished, or else you will have a lag. The aquifer is horizontal. Yes, it has to be confined because the equation is for confined. It has constant S. Yes, is not recharged. If you recharge, everything goes haywire. And this is assumed to be horizontal for simplification of mathematics, or else we cannot derive. Yes. Now, before I proceed, I think this is the next slide, and then this well function WU, that is Q upon 4 pi T, and this equation that expands. If you expand this infinite integral, it is like this: minus 5/7 minus log n U plus U, like this. For us it looks complex. For mathematician it looks very easy. Now my point is that for every value of U I put here, you have a computer programs. For every value of U, I will get a WU value. So I put one value of U, I will get a WU value. I put another value of U, I will get a WU value. So what will happen? I can plot a graph for so many values of 1 by U. If you get U, you can find 1 by U and WU. So this is a mathematically derived curve, and that is called Theiss master curve. And the most widely used by professionals. So what it says? It just says that for the well function, for this, it says that if you have one value of U here, this is this value. Another value of U here, this is this value. Third value, this is this value. So that well function is written as short here. So Q by 4 pi T, I have not written the integral, is WU, and U is R square S upon 4TT. So if this is fine, then you will see why this master curve, what is utility of this master curve. You just did the intellectual play, you have played on computer and created this, well, how this is useful. Okay, we will see how it is useful. So, and then the other equation was U is R square S upon 4TT. Let's arrange this, make T principal. Now then the question will be why you are making T principal and why you are making S principal. My dear, because this is only which I measure in field, that is drawdown, and this is only which I measure in field. So these are my observations. This drawdown every minute I measure. So I made them principal. For the endeavor of every science is to make life better and easy, and the endeavor of every mathematical manipulation is to make things simple, not complex. So with that approach, we have made this T here. So it becomes R square S by 4TU. If you break this, it becomes R square S by 4T into 1 by U. Now, and this is log n, this is S. Now if I have a liberty of putting a log n sign here, this is log n S equals to log n Q by 4 pi T. Log A into B is log A plus B. So log A plus log B. So log n S equals to log n Q by 4 pi T plus log n WU. And then ln T, log n T equals to, I have put this sign here. So R square S by 4T plus ln 1 by U. Now, this is a small s and this is capital S. This is a small s, so this is drawdown. This capital S is a storage coefficient. Actually, when we write with hand, we write it like this, so it is easy to distinguish. In computer, it was not possible, but so I keep saying. Now, what you are measuring in field? This is this T. You're in your pumping test, and what it says, this is a constant. Q is constant. Discharge is constant. As per your assumption, transmissivity is constant. As per your assumption, S is constant. If you want to see again, please read. transmissivity is constant. Then somewhere it must be written a storage coefficient is constant. The transmissivity is constant, and then storage discharge and decline head aquifer is horizontal, constant coefficient of the storage. So as per your assumption, this is constant, this is constant. So these are all constant. Now for students, on varies with T. In a very similar way, WU varies with 1 by U. This is an analogy. And now, so if I have a plot of WU versus 1 by U, this is a log plot. Log S varies with log A, okay. And then on a same log plot, yeah, that is called graphical solution to equation. And I could appreciate this only when I taught my daughter how to graphically solve these, algebraic equations, because I had forgotten this. And so this is a graphical solution. So you have a one plot where you have WU and 1 by U. And then on the same log sheet, if you plot T, if you put T here and S here, so yeah, it is here. So you have drawdown here and time here. So this is that Thais master curve, and you have another master curve where you have drawdown and time. Now what we do, this should be on a transparent sheet. Now what I do, I superimpose this on this, and this is what I am doing here. This is from Fetter's book. And when I do this superimposition, my endeavor is to bring all these dots here. So all these dots are on this line. This is called best fit. Now in this best fit position, from here, I can find four parameters, four values, let's not say variable, values. My x-axis will give 1 by U and T. T is here, 1 by U is here. So for any point, dam, any dam place you put, you can put in anywhere, but it should be somewhere here. You will get 1 by U and T. And so on y-axis, you will get S at drawdown and WU. No, I think I said go back. So yeah, you are here. So what I am getting from that plot, I know Q, I know 4, I know pi, I got WU value, I got, this is a small s, drawdown, I got a small s value, so I can estimate transmissivity. And then on the same plot, I got T value and I got 1 by U value, which reciprocal of which will be U. And from here, I got T, and R is the radial distance, which I have measured in field using a steel tape. And so I can estimate S. And that's how, from my purpose-built pumping test or purpose-built and designed pumping test, I can estimate the aquifer parameters using Thais equation. So now you will see many reports using Thais for unconfined aquifer. That's not wrong science. That's not that the hydrogeologist was incompetent, because the Thais method, I have clearly written it, for unsteady flow in confined aquifer can also be applied to unconfined aquifer, provided that all the assumptions are same. And the next is an important assumption, that the drawdown is very small in compared to saturated thickness. Then it was many thousands of iterations were done, and it was found that the results are good. The young minds must be having a question. Why you can't have a separate equation for unconfined? Why you always want to use Thais? You can have a separate equation for unconfined. Perfect, perfect. That's a very valid question if that is in your mind. First, we use thighs because using thighs is very easy. Then you must understand the other equation might be more complex. And thighs, using thighs type curve is readily available. There are softwares readily available. But for an unconfined aquifer, all flow dynamics are defined. It's not that they're not defined. The problem is that an unconfined aquifer response is a late response. Now, I don't know if I can introduce this, because if it sinks in your head, but let's try to make it simple and you so that you understand. Look, an unconfined aquifer, because there is a lithostatic pressure also, the instant reaction to pumping is like a confined aquifer. And then after some time, there is a drainage. There is a drainage from the aquifer. And after so many hours, the true unconfined nature, the aquifer, the aquifer release is as per the true unconfined nature of the aquifer. It's a slightly complex equations. We did some 4 pumping tests, 4, I think, yeah, 4, and we could find, we could fit in the unconfined equations, but they are all based on assumptions and they are all modification of thighs. And I must tell you, what I am teaching you here is what I have learned from practice. I'm not a PhD in hydrogeology, I'm a PhD in structural geology, and I am a practicing professional hydrogeologist, and I have picked up this as my subject for last 20 years. So I have learned my science while doing in field. It's an experiential learning. When we have used this unconfined aquifer data for estimation of the aquifer parameters, and I have tried to use the unconfined equations because they are all analytical models, the results was not many times perfect. But when we have used thighs in segments to an unconfined data, the results were realistic. And that's why I have put it purposely here, that you might, if you are, you can always treat an unconfined aquifer data with Bolton, Newman, and there are so many other equations. But if your saturated thickness is small compared to the overall thickness of the aquifer, treated with thighs, the results are good. So now this acknowledgement is required because I have picked up figures and modified from some standard textbooks, and it's on record. So I have put this because of this COVID-19 pandemic. This is purely for academic and teaching purposes. Figures are not as total from textbook. They have been modified with my Paint, MS Paint, and I have mentioned them explicitly in my presentations. The students are advised to read the textbooks for better understanding of the concepts. Thank you all for patience.
Thank you, Dr. Shekhar. Dr. Shekhar, are you there? Okay, I think Dr. Shekhar is not being able to connect with us. Thank you. Thank you, Dr. Shekhar. Thank you for your wonderful presentation. I would like to, there are a few questions. We need to start off.
I'm here. Can you hear me?
Yes, Dr.
Shekhar. I'm here. Can you hear me?
Yes, we can hear you.
Sorry for the inconvenience. Okay. Sorry for the inconvenience. I'm joining through my mobile data. I don't have any electricity here, and I regret the inconvenience. Sir, I have a lot of questions for you.
Yeah, please go ahead.
I have a lot of questions for you, sir.
Yeah, please go ahead.
Okay, Q&A question session. Okay, so I was able to see most of the presentation, but I have an that you must have taken up the mathematical concepts in detail. Title of the presentation with experience. Sir, my first question is researchers and students think of.
No, I didn't get your question.
Mathematical detail.
Mathematical detail?
Okay, without going into much details, much technical detail, how a
Okay. I guess
my first question is that without going into much details, much into technical things, how can a layman use these concepts for better hydrological studies?
Oh, perfect, Aditya. That's our endeavor to make science easy. Yeah. See, because before using a tool, I must convince you that the tool is sound. So I have used all this mathematics. Now, when you have to use, let's say, thighs, it's very easy. You have only two equations. Drawdown equals to Q upon 4 pi T WU, and U equals to R square S upon 4 TT. If you are, let us say, you must trust that these equations are right. That's why we derived it. They spoke so much about it. Now, let's say you are an MA Geography and you are doing a pumping test. So you can always use, you can have a double log sheet of thighs type curve. You can have a double log sheet of drawdown versus time. Just plot the data, do superposition, and then you fit in the equation and you get the results. The problem is when your results are not good, then you will need to break your head with an expert hydrogeologist. Similarly, almost everything, because this is a technical discussion, so you must be convinced mathematically. For say, the best example is I showed you that finite difference equation, not finite difference, the general equation for groundwater flow, those double partial differential equations, that is solved using finite difference approach. I took a class on mathematics way back in Roorkee, IIT Roorkee. I was convinced. Now, if you ask me to derive that finite difference, I cannot, though I did a training on that. But I trust that my mathematician friends did it right. And so I use them for all quantification. So it's like that. Tomorrow, if I have a problem, I will approach a mathematician. So if you are not interested to go in the depth, you can just follow the protocols, do it. But if you are stuck or if your results are not good, you can always go to an expert. It's like an MBBS doctor referring to a MS. It's like that. Yeah, Aditya.
Oh, yes, sir. Thank you. Sir, there are a lot of other questions, basically asking some basics of well hydraulics. I have a question from Mr. Mukhtar Hassan Ahmed from Aligarh University. Basically, he's asking that why thighs assumptions are so important.
Yeah, Mukhtar, nice. I think I'll just present again this. No, stop. No, it's sharing. Yeah. Can you see my presentation? No. Anyway. Now, thighs.
Sir, we can see your presentation. We can see your presentation.
Okay. So I will bring the assumptions and then they are following. Now, see, Mukhtar, the moment I say the aquifer is homogeneous and isotropic, I have got rid of two troubles. I need not mathematically estimate K for different parts and K in different direction, let us say, or transmissivity in different direction. Because, see, all science starts from simple to complex, not vice versa, from complex to simple. All our science starts from an approach where you use the simplest and say, let us say you say, oh, but my aquifer is heterogeneous. Okay, fine. First you assume it as a homogeneous, then you divide your whole aquifer into different homogeneous units, and estimate for them. Similarly, it is for isotropic. Then infinite aerial extent. Why infinite aerial extent? Because maybe this, yeah, this one, or okay, presentation mode. Yeah, if this aquifer is not of infinite aerial extent, and let's say there is a barrier here, what will happen? That it will show its effect. This cone of depressor will decline at a very fast rate here. So then you cannot estimate this. That's a different effect. So every assumption then well penetrates the entire thickness. This we have because if you don't penetrate the entire thickness, then an additional head loss has to be estimated because of partial penetration. So that increases another load of work. So better you make a well which penetrates the whole aquifer. Then T is constant, because if you make T variable, then you cannot estimate that from this equation. You cannot estimate that. Then the next one, it has infinitesimal diameter. Yes, I think this needs understanding. Look, if you have a dug well, you might have had a look at a dug well. Now, if you take water out from dug well, one bucket, then there is no change in head. Why? Because it has a storage. Now, I don't want that when I am doing a pumping test. I want that whatever response, it should be the aquifer's response. It should not be the storage response of the tube well. So if the dia is long, if dia is big, then it will have its storage effect, and the head difference which we measure will not be the correct head difference in aquifer. So I want to make the diameter as small as possible. And that is why the next is linked to it, that water removed from a storage is discharged instantaneously. There is no lag. Everything, because see, the best thing would be to make an imaginary tube well and pump, but that's not possible. You have to put a tubular structure. So you want to minimize the effect of artificial structure and at the same time estimate the true aquifer parameter. Horizontal, because if it is inclined, then the equation will have to factor in the head difference because of the elevation difference, which are not factored. Confined is a precondition. Same thing with coefficient of the storage, like that with transivity. If it is recharged in between, then another factor has to come in the equation, plus minus W. That is not there. So in a nutshell, and it is horizontal because if you go back, the drawing makes it horizontal. If you make it inclined, then the symmetry of the cone of depression changes. See, these are all analytical models which are based on a set of assumptions. And Mukhtar, if the other day you become a hydrogeologist, and using these equations, you get a weird result, you get a wrong result, or maybe something which is not correct, then please examine these assumptions, whether they were violated or not. I think then it makes you look for a simpler system which you quantify, and then there are modifications in Theis equation, that is Ferris et al. There are many which then takes care. Partial penetration, there are modifications. So you can do that, but to start, you must start from simple. Okay, Aditya. Yeah, hello. No, I think. No.
Can you hear me now?
Aditya.
Okay. So the next question is from Mr. Abhirup Bose, Jadavpur. So he is basically asking about the phenomena which almost everyone who has worked in well hydraulics have experienced. There is always some fluctuation in the groundwater quality, the salinity, when the pumping test is conducted. So when a pumping test, especially during a long duration pumping test, we see that there is always some variation in quality. So his question is basically that how these changes can be accounted for? First question. And secondly, he wants to know that how well hydraulics can affect the coastal aquifers and its quality. That's the crux of his questions.
Yeah. What was his name?
Mr. Aviroop Bose from Jadavpur University.
Anirudh.
Aviroop.
Okay. Aviroop. See, first of all, the well hydraulics, one of the fundamental things is that it takes, these all equations are for constant density. Means you assume that the water has a constant density. When the TDS of water changes, that is the salinity of water changes, then density changes. And as such, sensu stricto, these flow equations will have to be rewritten for a different density. The cause and effect relationship will be different. Let's make it very clear that these are constant density equations. Now the question is how, it has come. It's a good question. We can plan an experimentation, and I am sure that you interpret the set of data till the water had an average TDS for aquifer parameters, and then the next set of data when maybe there was an upconing from bottom. And if you remember the definition of hydraulic conductivity, which gives rise to transmissivity, that it is CD square rho G by mu. That is hydraulic conductivity. CD is diameter, rho is density, and G is acceleration due to gravity, and mu is viscosity. Now the moment your water becomes saline, the density and the viscosity changes, and so hydraulic conductivity will have a different value. It's a very valid question. Somebody has to experiment and verify this, that you have a set of data which was for this particular TDS, and then another set of data for this TDS. I am sure you will get two different hydraulic conductivity values, and then the question is which one to use. Yes, the one which comes later on will be more valid for a longer duration of pumping test, for a longer duration of extraction. So that call we have to take as a scientist. And then what was the second question? In coastal areas? Yes. Yeah. See, hydraulics is same, whether you do it in inland or coastal area. The fundamental equations are same. Only thing is that you must remember is that the fundamental flow parameter, that is hydraulic conductivity, is a function of media and fluid both. So the moment you go to coastal areas, if you have seawater intrusion, then the fluid nature changes. And as such, let me put it like this. A coastal aquifer with fresh water will have a different hydraulic conductivity, and a coastal aquifer with a seawater will have a different hydraulic conductivity. And that is for us to estimate and establish that difference and use in quantification. Yeah.
Yes, sir. Thank you, sir. So can I continue with the questions?
Yeah, Aditya, you know I enjoy.
Okay, okay. So there is a question from Mr. Mohammed Tariq from Schlumberger. His question is that the pumping test is rather a difficult and an expensive procedure. So are there any alternative methods, some modeling methods or some kind of methods that could be utilized to estimate the hydraulic conductivity and all the other parameters without doing the pumping?
Yeah, he is Mr. Tariq.
Mr. Tariq from Schlumberger.
Schlumberger is a big company. It shouldn't be miser in spending money. But anyway, see why we say pumping test for an aquifer parameter. Yeah, there are many alternatives. You can have a permeameter in lab and estimate the aquifer parameter. Just let's say I run a lab, I have a permeameter, constant head, falling head permeameter, and I ask you, oh, don't spend this 5 lakhs or 10 lakhs on a pumping test, 20 lakhs, bring the sample. Now, for Mr. Tare, you must keep one thing in mind, that the very aquifer parameter we are estimating. And again, I will say that equation. Hydraulic conductivity equals to C d square rho g by mu, where C is a constant, which is a function of the grain packing and sorting. Now, if I pick my sample from field, so I dig it, I drill it out, and I bring it to lab, I have totally changed the sorting and packing of the material. So whatever hydraulic conductivity or then the related transmissivity parameter I will estimate will never be a true value, because sorting and packing has changed while drilling it out and while transporting it. First. Then second, you can say, oh, then why? Okay, fine, I will do a slug test. Put a bucket of water and estimate the aquifer parameter. We can do that. Many of us do it professionally. But any aquifer, see, it is, let's put it in a normal way. How do you recognize the nature of your best friend when you are with him for a very long time? Then you understand the response relation under different stress conditions. Slug test is a very small time reaction. Many times the aquifer, for an unconfined aquifer, it is nothing. It is an eyewash. It's an eyewash. Maybe many experts will disagree. I don't mind, but it's an eyewash. For a confined aquifer, to some extent, yes, but that never gives a true representation. Because, see, why unconfined aquifer it's an eyewash? Because the unconfined aquifer is never revealed in so soon. It takes time. So the best alternative is, it depends on your project cost. If your project, if you are, let's say, if an organization is investing in making 100 tube wells, and one tube well at the rate of 50 lakhs or 20 lakhs or 30 lakhs, it's a 50 crore investment. It would be worthwhile to go for suitably designed pumping test. But if you want these values for a maybe investment of 1 lakh, 2 lakh, 3 lakhs, 5 lakhs, then you can go for the slug test, or you can go for these permeameters. But before I summarize, the organization called Central Groundwater Board does it in a routine way, and they have a repository of data in terms of basic data report. The accessing that is a problem, but I think now government has initiated, and I think they may be available in public domain, and that can always be used. For me, if you should always prefer in situ pumping.
Yeah. Okay, sir. So there are a lot of smaller questions as well. There are some questions about the anisotropy and isotropy, how we will assume that what kind of aquifers are considered to be anisotropic, and what are the parameters to check them. But I'm just going to compile it into one general question, which is, what are the basic things we need to look into once we start, or once we plan to do a pumping test or aquifer parameter test?
Yeah, perfect. See, first of all, you will do well performance test, that is warm up to maybe to assign pumping, discharge, and other things. First of all, diagnostic. I didn't cover that here right now, but I'll quickly add that diagnostics of the data. Now, even if your lithologs say that it's a confined aquifer, many a times the lithologs are very local in nature, and the clay lenses are very small. The best is that you get a data. First, you put a pumping tube well, then you have an observation wells, you have the data. Till then also, I must say, you will never be sure that this is a confined or unconfined aquifer, unless and until the plot of S versus T on a log-log sheet or on a semi-log sheet conforms to the diagnostic plots of a confined aquifer. Look, aquifer, then only you can use Theis equation. Look, aquifer confinement is not only lithologic confinement, it has its connotation in terms of pressure response. So I don't have that slide here right now, but quickly I can use Theis. The best thing is that you have planned a slide. That's fine. That's very easy. And for beginners, the problem you must put your observation wells within radius of influence. Don't put them so far off that there is no signature. So and then you will ask me how radius of influence is to be estimated. For a known value of k, it can be estimated by reverse calculation. So that's a common sense. Let's say my data here, the data of S and T I plotted. That has happened with me. I played with all this data, and suddenly the data goes like this. Or maybe suddenly the data. Oh, let's see. It had happened with me. The data is like this, and it goes like this. Then the response is not confined. Though lithologically the aquifer looks to be confined, but the hydraulic response says that this confinement is very local. And this deviation is because of some either leakage or a delayed yield phenomenon of an unconfined aquifer, which after some time may give rise to an S-shaped curve. So first you make a lithologs, do well performance test, estimate the pumping discharge, ensure that your observation wells are within radius of influence, work out the radius of influence from published K or from a literature for the similar sand material or similar silt material. Then maybe you start your pumping test, get the data, don't jump upon, plot it, match it with the diagnostics, and then make a statement that is a confined, semi-confined, or unconfined. If required, repeat the test, or use the data for estimation. Yes, Aditya.
Sir, there are still a lot of questions going on. People are more excited. So what I'm trying to do is I'm trying to compile some general questions into common question. So there is this one question also. There are different types of terrains and different forms of aquifers. Yesterday we had we were discussing about aquifers and aquifer mapping. So there is this one question which can be integrate all the smaller questions which are coming. That how as hydrogeologists, firstly, working in different terrains, we can use this data for groundwater resource development as well as for contributing towards societal development.
Yeah. See, why I am in water science is because it has direct societal value. There is a scope of service to humanity. So all water science has direct societal relevance. And I think today it's one of the sought after science. Now the question is, when you are working in different terrain, how you use the data for welfare of the humanity and the society at the local scale. Yes, and then how all the fundamental science is used there. See, India is a wide, diverse country. You have so much of diversity. So in a hard rock terrain, there will be a different set of parameters. In an alluvium, there will be a different set of parameters. They have to be used. But at the end of the day, you can always see there are ways of solving a problem. If a problem is too big and too complex, you break it into set of simpler problems, solve them in a homogeneous domain, and then bring them together for a mosaic presentation of the heterogeneity. And that's the approach where we have to adopt when we work for a country at a country level, and for a country like India, where we have to work for different homogeneous domains and then compile that data and bring it as a one whole united data, maintaining the distinct heterogeneity. It is something like the federal setup of the Union of India. Water resources and water quality. In fact, if you read deeply, water resource estimation, that is CGWB report, I will advise some of the young hydrogeologists, or some of them who are beginning their career, must use this once for their estimate. It has parameters that this is poor quality area, there will be no estimation and things like that. Unfortunately, arsenic and fluoride and other things are not factored in because it's a quantification. They cannot be factored in. And I must tell you that it's not that all groundwater is polluted. There are isolated patches. Might be that helps us in writing paper, that we say that, look, I have found these trace metals and so many things, but still the Indian aquifers have some of the best drinking waters and they're being used. Because we highlight the problem, that's a different thing, but at the same time, the aquifers are still good. So we can do a resource estimation like it is done in Central Groundwater Board for different states, different territory, different talukas, and then a mosaic is prepared, and that becomes the first approximation, and that is readily available in public domain. It can be downscaled. I think when I was assigned a small task of there was a consultancy project for DMRC in Delhi. So what I did is that I estimated again the resource for that, but using the same data from the CGWB resource assessment, not by downscaling, but by re-estimating. So that can always be done. But yes, at the end of the day, it is a science. There are experts, but the science is a broad science. It needs to be integrated with social scientists, economists, and from lab to field is the toughest task. There it's the non-governmental organizations, private companies, and so many stakeholders, they come in picture. So it's a long way, but still water science has changed life of India much. That's a fact. Yes. Aditya.
Sir, thank you so much. Yes, sir, thank you so much. Can you hear me?
Yeah, Aditya,
hello?
Thank you. Yes.
Okay, sir, sorry. Sir, these are one of these disadvantages of conducting an online seminar on a national level. Will always be, there will be always some disruptions and disconnections. So unfortunately today I was not able to hear you, but it's always been a pleasure hearing from you, and I can go on because a lot of people are keen and they are still sending the questions, which we'll forward to you afterwards. But thank you, sir. Your experience as a hydrogeologist in CGWB and as a teacher was definitely reflected in whatever I was able to see, and it's always a pleasure to have you, and always wonderful to hear from you. I hope a lot of our students and a lot of our attendees here must be enriched by this particular session. Thank you again, sir, for your time. And now, continuing with the process, I would invite Dr. Ghoshal to start proceeding for the next session by Professor B.B. Bhattacharya. Dr. Ghoshal, can you hear me? Thank you, sir. Thank you so much. Dr. Ghoshal, can you hear me?
Yes, Dr. Shekhar, can you hear me? Am I audible?
Yeah.
Yes, I am audible, sir. So the podium is for you now. I am logging off.
Thank you so much, Dr. Sarkar and Dr. Shekhar also. Dr. Shekhar, it was very nice to hear from you for the first time. Thank you for the wonderful presentation. sir, and it was very informative. And I am sure that we have learned a lot of new things from your presentation. Thank you so much, sir.
Thank you.
So we are actually having a lot of connectivity issues. So sorry for the inconvenience. Good afternoon, everyone. I welcome you all again to the fourth session of this two-day webinar on applications of conceptual hydrogeology. So before I introduce Professor Bhattacharya to you all, I just want to let you know that he is not at the best of his health, but he is very much enthusiastic and very much interested in interacting with all of us. So I would like to introduce Professor Bhattacharya to you. He was a professor, dean, head Department of Applied Geophysics, and director in IIT ISM Dhanbad. He is an emeritus professor, India INAE Distinguished Professor in Bose National Center for Basic Sciences, Kolkata. He was a visiting professor in Department of Physics in University of Alberta, Canada, and also in the Department of Geology and Geophysics in University of Wisconsin, USA. He was also the leader of the 4th Scientific Indian Antarctica Expedition by Government of India. Professor Bhattacharya completed his BSc in Physics and MSc in Geophysics from Banaras Hindu University in 1961. He completed his PhD in Physico-Mathematical Science from Leningrad State University in Russia in 1974. In his earlier days, he had worked in Geological Survey of India and also as a scientist in NGRI Hyderabad. He achieved many important awards and honors like National Mineral Award from Department of Mines, Government of India, Dr. Coggin Brown Gold Medal on Earth Sciences from MGMI. He received the Decennial Award from Association of Exploration of Geophysicists, and he was the chairman of Computer Society of India, Dhanbad chapter. He also delivered Prince Mukharamja Endowment Lecture in Indian Geophysical Union held in Madras University in December 2003. He was also the recipient of Distinguished Professors Chair by Indian National Academy of Engineering in 2006. So it is now my great pleasure to welcome him, and I request sir to deliver his lecture on geophysical investigations for groundwater in hard and soft rock terrains. I can just request for just few minutes, 2 minutes for him to get ready for this lecture. Thank you.
Greetings from Professor B.B. Bhattacharya to the delegates of the participants of delegates and participants of the seminar on groundwater, geophysical exploration for groundwater. Normally, I should have physically present there. Normally, I should have been physically present there to deliver the lecture, but somehow it's that I am not in a position to do so. So, anyway, the alternate arrangement has been done, and let us hope that it is a satisfactory arrangement. Basically, the topic is that geophysical investigation for groundwater or hard rock and soft rock terrain. Generally, the basic theory is that it is assumed that all your measurements are done on a flat surface, and Earth is divided into layers of different resistivity or electrical conductivity. That has been working quite satisfactorily. So, Mother Nature is very complicated, and occasionally we do get hiccups. Now, the issue is that broadly, if you look at the layers for groundwater, normally for hard rock terrain, you will get a two-layered resistivity or two-layer seismic refraction. In hard rock terrain, seismic refraction works pretty well because there is a velocity contrast, seismic velocity contrast. But in case of resistivity, the response has been quite satisfactory for most of the cases. Now, what exactly has happened? If you take simple cases, you will see that many of the cases, so there are two-layer cases, there are three-layer earth, there are four-layer earth. Now, I would have loved to give details, but I'll cut short and make it a bit simpler. Now, what exactly happens? That suppose if you take a three-layer earth with a resistivity contrast between the various layers. So if the first layer is a higher resistivity and second layer is relatively low resistivity, which is a common case in soft rock, Indo-Gangetic Valley, and third rock is a slightly higher resistivity. And in that case, the earth will look at the response will look like first layer higher resistivity, second layer low resistivity, third layer higher resistivity. So it is called H type of rock, H type of response, which is quite common in relative Indo-Gangetic Valley, right from Punjab to Brahmaputra Valley. Now the question is, if the first layer resistivity is, second layer resistivity is not low, if it is for some reason high, you see resistivity will depend upon porosity, permeability, and saturation. If it is well saturated, it becomes low resistivity. If it is not that well saturated, it becomes somewhat more resistant. So these are the, and then in addition to all this, then there is another type of curve that I will get it. That is called K type of curve or bowl type of curve. No, bell type of curve. That is then there is another type which is a descending type of curve. I am assuming that the earth consists of three layers. Top layer, middle layer, and last layer extending up infinity. Then there is a ascending type of curve, which is gradually rising in resistivity. They call A type of curve. So broadly, if the earth is divided into three layers, then there are three types of curve: H, K, A and Q. So this is the basic format. I'm getting a bit tired. I hope you'll be ready. So I would have loved to talk to you very much further. But somehow because of my health problem, I thought I should excuse myself.
Thank you so much, sir. Thank you for your efforts and taking all the pain. I would thank all the participants for your patient hearing. We are not taking any queries for this session, unfortunately, and the queries which were not discussed in the sessions would be conveyed to the concerned speakers, and we'll try to get those queries resolved as soon as possible. We hope that you have enjoyed and learned a lot of things from these sessions, which will help you in your future. Our main objective of conducting such webinars was to enrich our knowledge in different aspects of hydrogeology. And as webinars has now become the new medium to spread knowledge, we hope to conduct such events and lecture series in subsequent months as well, with distinguished hydrogeologists and geoscientists from the different parts of the country. So before ending this session, I would like to reiterate that fact that any query related to the session and anything related to us should be given in the WhatsApp group, and we would be providing a feedback form in half an hour time. And we would request you all not to leave the group right away because we will be giving subsequent information regarding the webinar. In the end, I would like to start off with a vote of thanks. Respected Professor Bhattacharya, Dr. Shashank Shekhar, Professor Pradip Kumar Sikdar, Dr. Dipankar Saha, other esteemed guests, distinguished faculty members of the Department of Geology, Presidency University, dear students and participants from all across the country. A very good afternoon to you all. As we come close of this two-day webinar series on applications of conceptual hydrology, it is my honor to acknowledge the people responsible for making the event a great success. Firstly, on behalf of the Department of Geology, Presidency University, I would like to thank Professor Bimalendu Bhushan Bhattacharya for enlightening us with a short and crisp lecture that highlighted the amalgamation of geophysics with hydrogeological studies. I must inform you all that again, that Professor Bhattacharya has delivered this lecture despite not being at the best of his health. Sir, we wish you a speedy recovery and hope that we also pursue our work with the same passion and dedication that you have over here. Thank you so much for taking all the pain. Am I audible? Am I audible?
Hello?
Can you hear
Yes,
me?
you are audible. Yes, you are audible.
Okay.
Yes, I'm audible.
Yes.
Okay.
You are audible. You are audible.
Okay. I would also like to thank Dr. Shashank Shekhar for joining us today and sharing his views and experiences with us. Sir, I'm sure that your work would enrich the knowledge of all in attendance and scintillate the scientific minds amongst us. I must also mention our deep sense of appreciation for Professor Pradip Kumar Sikdar, who has always been encouraging us throughout with his valuable opinions and giving us the insight of his vast knowledge and experience in the field of hydrogeology. Further, I would like to profoundly thank Dr. Dipankar Saha for his relentless support and gracious attitude, sir. Sir, I know that in spite of your busy schedule, you have been kind enough to not only to conduct a session in this event, but also guided us in this endeavor from the very beginning. A special thanks to the faculty of this department, especially our head, Professor Gautam Ghosh, and Dean of Faculty of Natural and Mathematical Sciences, Professor Joydeep Mukhopadhyay, for their encouragement and valuable suggestions, which helped us making this webinar a grand success. I would also like to thank all the students, volunteers for this event, Sheikh Bande Ali Mullah, Alifia Ipkar, Shreya Chatterjee, Shoumi De, Diganto Sengupto, Pradeep Pal, Animesh Mondol, Odri Boshak, and lastly Debaroti Shaha, who have been toiling for days to ensure smooth running of this webinar. Finally, I would thank all our participants that included some of the leading researchers and stakeholders in the field of hydrogeology for their presence that made this two-day webinar an unforgettable experience. With this, I close this session with a gratitude for all present here today. Thank you and have a nice day. And lastly, again, I want to repeat, participants, do not leave the WhatsApp group right away, because we will be providing a feedback form in which we need your opinions and how to make better webinars and your opinions and suggestions in half an hour time. And request not to leave the group right away again, because you will get the subsequent informations for regarding the webinar. Thank you. Thank you so much.
Hello, Utsav. Hello, Utsav.
Yes.
Hello. Yes, just convey our regards, deepest regards
to
Professor Bhattacharya.
Sure, sir. Sure, sir.
On behalf of the department and on behalf of the Defense University.
Sure, sir. Okay, sir.
Sir, please on behalf pay our deepest regard to Professor.
Yes. Thank you very much. I also wish you all the best. And I am sure in future we are going to interact much more effectively.
Okay, sir. Thank you. Thank you. Have a nice day. Thank you.
Thank you. Thanks to the organizers.